We're going to be talking about distance vector protocols such as RIP and IGRP, and just basic guidelines these protocols follow, such as how they populate the routing table, routing loops, and how RIP and IGRP avoid routing loops, and when to use RIP and IGRP as routing protocols versus something like OSPF. Now let's go over routing table population with distance vector protocols. Right now we've got three routers here, router A, router B, and router C. And the routing tables are going to start off with only the directly connected subnets. So router A would know where network 99.8, network 99.32 are. B would know where 99.16, 99, that's 96, 99.4, and 99.32, because it's directly connected to those subnets. Router C would know where 99.24 and 99.40 are located. Let me fix that right there. So it all starts off with the routers having the directly connected subnets in the routing table. And again, they get that directly connected subnets when you configure an IP address on an interface in the subnet mask. They do the ANDing process, which is comparing the IP to the subnet mask, and come up with the subnet address or network address, and they put that in their routing table. So 99.8 and 99.32 are going to be in A's. Now when I enable RIP or IGRP, they function pretty much the same as far as populating the routing table. So we'll use RIP as an example. I go in and enable RIP. Now what happens is when I enable RIP to route. Let's say on each router I have to do that, router A, router B, and router C. I have to enable it to route for the entire 99.0.0.0 network. And so any interface on the router that is a part of the 99.0.0 network will participate in RIP routing protocol, meaning they'll share information with other routers based on the set of rules specified with routing information protocol. So what that means is this interface here, as well as this interface, are both part of the 99 network, meaning they have a 99 in the first octet. They're both going to participate in RIP. What they're going to do is they're just going to start broadcasting every 30 seconds. They're going to broadcast these routing tables out of all these interfaces. I mean, there are things that I can do. I could turn off RIP on this interface and tell it not to send information out of this interface because there aren't any routers over here. But by default, it's going to start sending stuff out. Router B, when I enable RIP for network 99.0.0.0, it's going to start sending out all its interfaces, and C, same thing. So what happens is router A sends 99.8, 99.32 subnets over to router B. Router B looks at that information. And router B uses the metric called a hop count. So what happens is router B goes, okay, I'm getting some information and it's coming in through my serial 0 interface here. And let me see what this information says. It says 99.32.0.0, and that next hop router has a cost of 0. But hey, I already know where 99.32 is. I have a connection to 99.32 out of my serial 0 interface, and I have a cost of 0. So that guy, if I wanted to send a router A to get to 99.32, it would cost me 1, so I'm just going to disregard that information. So B just disregards that information. And then he looks at 99.8. And he goes, okay, 99.8.0.0, I don't have that in my routing table. The update came in through the serial 0 interface. So if I need to get to 99.8, I better go out of my serial 0 interface. And he adds it into his routing table and says, hey, This guy has a cost of 0, so RIP simply adds 1 to the previous router's cost. So my cost is going to be 1, meaning to get to 99.8, it's 1 router away. So it has a hop of 1. Router B takes its routing table and sends the whole thing over to C. And C goes, oh, 99.40, I have that. I don't need that. What I don't have is 99.16. I don't have 99.32. And I don't have 99.8. So what's going to happen based on RIP, it says all 3 of these updates came in through the serial 0 interface. So I know if I need to get to these these destination subnets, I better send out of my serial 0 interface. The previous router had a cost of 0 to get to 16, so my cost is going to be 1. He had a cost of 0 to get to 32 subnet, so my cost will be 1, meaning 1 router away. However, for 99.8, router B's cost is 1, so router C is 2 routers away. So he's 2 hops away, and he puts a 2 in his routing table. The pre-existing routes have all costs of 0. And again, it just associates the interface with the cost. Sent back down, 99.8, or router B learns about the 99.24 subnet. His cost is 1, serial 0. And this guy eventually will learn about every subnet in the network from router B. So he'll learn about 99.16 and 99.40 and 99.24 subnets. And the only one, these both have a cost of 1, and to get to 24, cost of 2. They will all go out of his serial 0 interface. So now that all the routing tables are populated, again, you have a client machine here. If he wants to get to this machine over here, he wants to ping him, or whatever he's trying to do, when he addresses it at layer 3 with the IP, the destination IP address is going to be maybe 99.24.0.10. He'll put that in there as the destination IP. And what will happen is router A will compare 99.24.0.10 to the subnet mask of 255.248.0.0, and he'll figure out and go, oh, that is subnet 99.24.0.0. Let me check my routing table. There it is. I can barely read it, but there's 99.24. And it says I have to go out of my serial 0 interface, and that router is 2 hops away. So he'll send it out of his serial 0 interface. Router B will do the same thing and go, oh, 99.24. Again, barely read it. There it is. I have to go out of my serial 1 interface, it should say, and that is 1 hop away. So he'll send the packet out of this interface. C will do the same thing. Go 99.24. I can read that pretty well. It's on my Ethernet 0 interface, and I am directly connected because my cost is 0. And he'll send it out to this computer. So these protocols, distance vector, simply broadcast their routing table out of all interfaces associated with the published network. And what I mean published network, when I turn RIP on, I type router RIP, and then the only other thing I have to type is the network that I'm publishing, and I type network 99.0.0.0, and that publishes the network. And I do that on each one of these routers. And what happens is every interface that's a part of the 99 network, which is all of these interfaces in this slide here, will participate, meaning the router will start broadcasting these routing tables out. Everything they've got, they send it. If it's RIP, they send it every 30 seconds without fail. The routers will use what information they can from the routing table. Any information they cannot use, they dump. I have cleaned up this slide so we can start talking about routing loops and loop avoidance. I'm just going to use routers B and C for this. So let's take a look at router B's routing table. His routing table is going to have 99.16, 99.40. Just pretend that this does not exist over here. He's also learned about 99.24 from router C, and he knows to get to 99.24 subnet, he's got to go out of serial 1 interface, and the cost is 1 hop away. Router C, to get to 99.24, goes out of his Ethernet 0 interface, and his cost is 0 because he's directly connected. So what happens is router B just keeps bombarding router C every 30 seconds with his routing table. Router C looks at it and goes, okay, I know where 99.40 is because that's on my serial 0 interface and I'm directly connected to it. I don't know where 99.16 is, so I'm going to put that in my routing table. I'm going to have to get out of serial 0 to get there, and it's going to be 1 hop away. And I see that you've got 99.24 in there with a cost of 1. I have a cost of 0. I'm directly connected to that. So I'm going to ignore that information. Now, it seems obvious that C would ignore that information. But what C doesn't know, he doesn't know there might be another router D here with a connection to router B. So router B might have a path directly to the 99.24 subnet in a different way. C doesn't know that. All C knows is that router B does have a path to get to the 24 subnet, but it's not better than his. He's directly connected, so he ignores that information. Now, the problem. What happens? This link goes down for whatever reason. As I said in another video, somebody can trip over these things, unplug it just to be mean, rodents, whatever. Whatever the case, this connection is down at the router. So no one can get to 99.24 except for the people that are already in the 99.24 network. So they're pretty happy because they can talk to each other, but they're still not going to be able to get out. No one could get to 99.24 right now. So C's like, all right, I can't get there. Let me mark that as down. And he's bummed and he can't get to 99.24 anymore. And all of a sudden, router B saves him. 30 seconds have gone by. Router B sends his table over before C was able to tell him that he can't get there to 99.24 anymore. If C tells router B that he can't get to 99.24 anymore, B is going to mark it as down. But if he hasn't had the chance to tell router B that he can't get to 99.24 anymore, then router B is going to update him and say, hey, I can get there. And I'll go, oh, a new way to get to network 99.24. He doesn't realize that there is no new way and B has to go through him to get there. He just sees that B has a way to 99.24, so he's going to try to use it. And since B's cost is 1, his cost is going to be 2. And he is going to go out of his serial 0 interface instead of his Ethernet 0 interface. And what happens is, when he sends his routing table back over to B, B is going to go, whoa, you raised your prices. You have a cost of 2? My cost is 3 now. He'll send it back over. All of a sudden, his cost is 4. His cost is 5. His cost is 6. And this is the redundancy of a routing loop. Any traffic will just bounce back and forth in there until router B gets up to 15 or so. This guy will look at it and go, 16? No way. I'm not going to use it. Can't get there. It's called the infinite distance metric for RIP, and it's 16. They will not put a path that's 16 routers away in the routing table. So this is what's called a routing loop. Now, obviously, a routing loop is not good, so there are some things that have been implemented that RIP and IGRP use to avoid these routing loops. Let's take a look at them. There are a few different ways that RIP and IGRP, or a few methods RIP and IGRP use to avoid routing loops. split horizon with what's called poison reverse. Let's take a look at what split horizon does. I've simplified this slide again to demonstrate split horizon. So router B is going to have 99.24.0.0. He has to go out of serial 1 to get there, and it's going to be a cost of 1. C has 99.24.0.0 in there. He has to go out of his Ethernet 0 interface, and his cost is 0. What split horizon does is it says it is never useful to send information about a route back in the direction in which the original update came from. So B found out about network 99.24 through the serial 1 interface. So before he sends his routing table out of that interface, he's going to remove this information. So all C will see is 99.16 from router B, 99.32, as well as 99.8 if that's in there. So he'll be able to use that information, but this information will be removed because the update about 99.24 came in through serial 1. So when B sends information out of serial 1, it's not going to have that 99.24 network in there. So if this path goes down, C will not think that B has a path to network 99.24. What the poison reverse does, the split horizon with poison reverse, is C will mark this as down if this goes down. And what's going to happen is he's going to tell the other routers that this path is down. So he'll tell B that it's down. B will mark this entry as down in its table, and the poison reverse is, okay, since you're marking this as down, it's okay to send the information about 99.24 to C. So he will send information about network 99.24 out of this interface, only to let C know that he knows the path is down. That's the poison reverse. It's kind of like a say, okay, I got it. I know the path is down. Don't worry about it. I won't send it to anybody else. So that's the poison reverse part. And that has to overcome the split horizon rule, because split horizon says you can't send information about a network back out the interface in which the original update came. 99.24 update came in through serial 1. C marks it as down. Poison reverse says, okay, since you're going to mark it as down, you can let C know that you are marking this path as down and that you've gotten that update. And that's the poison reverse part of split horizon. Let's take a look at another one. So that was split horizon with poison reverse. Now let's talk about route poisoning. And that's basically what C is going to do when that particular path goes down. He's going to say, hey, 99.24 is down. He's going to mark it with an infinite metric value, meaning, hey, it's 16 to get there. You can't get there. 16, as far as RIP is concerned, is very far away and unreachable. So if you're 16, you are unreachable. So what C is going to do is mark that with an infinite metric value, pass that information along to B. B is going to mark it with an infinite metric value, saying, hey, I can't get there. Pass the information along to A. Convergence is the amount of time it takes for B and C to realize that 99.24 network is down from the time it goes down. Convergence. It's the amount of time it takes for everybody to get updated with the appropriate information. So that's route poisoning. Another thing that happens is a hold down timer gets put into effect on router C. So since C marked this as down, what's going to happen is he will not accept any changes to his routing table concerning network 99.24 until he knows all of the other routers have been updated. So as long as it takes for convergence to happen in this network, C will not take any new information about network 99.24 just in case, because he doesn't want to start a routing loop. He would, however, take information if there was a better cost than his original cost. But his original cost was 0. So you can't get better than that. So what's going to happen is he's going to lock down this entry that 9924 is down until he knows everybody else has been updated with the fact that that route is unreachable. The last one is triggered updates. To speed up convergence, remember RIP sends out its routing table every 30 seconds by default. So the route might go down just after he sent his update. So it's got to wait 30 seconds here. Then all of a sudden B gets that, and he just sent his, so it's got to wait another 30 seconds before he sends out. So it could take a full minute for a router 2 routers away to get the information that network 9924 is down. In the meantime, router A might still be trying to send a bunch of information over. So what happens is a triggered update says, hey, if a route is poisoned or something like that happens, let's send it off immediately. It triggers an update. What that does is, as soon as this path goes down, boom, update goes. B gets it, it's marked as down, boom, update goes. So convergence takes place a lot more quickly, so there's no confusion in the routing environment. So that's triggered updates. So again, with these routing loops, our RIP and IGRP protocols use split horizon with poison reverse. They poison routes and say, hey, these routes are down. Tell the other routers about it. They use hold down timers. Say, hey, I'm not going to listen to you for a little while until I know you've been updated with the appropriate information. And then if something does go down, a route goes bad, whatever, it triggers an update to happen immediately to speed up convergence. So we've talked about these protocols. Let's talk real quick about when to use these protocols. RIP and IGRP are very easy to use. So RIP or IGRP equals easy. You do not want to use these in networks larger than 50 routers. That's the cutoff, 50 routers, and that's per Cisco. Now, the only other snag is IGRP is a Cisco proprietary protocol. RIP is vendor neutral. So if you have non-Cisco devices, you're going to want to be running RIP. If you have all Cisco, you can run IGRP. We have talked about distance vector concepts, how the routing tables populate, routing loops, and how to avoid them, and when to use these routing protocols.